Okay.
Learning while treating. And welcome, Walter, and welcome everybody to the mDOT webinar series here today on April 3rd. And we're excited to have you, Walter. Thank you for joining us today. And as you know, the recording of this presentation will be shared on the mHealth Hub for asynchronous consumption later. So I'm sure plenty of people will be able to see it both now in the present and in the future, and we'll have a curated version of that we'll be sharing out later. So currently everyone's microphones and cameras are muted so that we can move forward with the presentation expeditiously. And toward the end, when your Q&A segment opens up, we'll go ahead and open those back up so that people can offer you questions. If there are any questions now, please let us know. We have a Q&A session for all of the participants, or Q&A segment here on the Teams app. So please put your questions there, and they will be read out at the end. But Walter, I'll pass it off to you unless there's anything else you need from us. And please feel free to get started.
Thank you so much. And thank you, Vivek, for the invitation. So I am Walter Dempsey. I'm an associate professor now in the Department of Biostatistics. And as Vivek mentioned, I went through a lot of different phases involved with mDOT. So I was first a postdoc with Susan Murphy, then a scholar as part of mDOT. Then I was an assistant professor, then I was a mentor, and now I'm an associate professor. So I've gone the whole spectrum, and I'm very appreciative to come back and give my perspective on a few different topics. I think, Vivek, I have your list of things that you asked me to talk about, sort of reinforcement learning algorithms as well as causal inference in the context of mHealth and adaptive interventions. And so my goal today is to really spend the next about 45 minutes talking about a few different projects we've worked on from the perspective of developing and deploying these learning algorithms for real-time health optimization, and then thinking a little bit about post-study, how do we actually analyze the data from these studies that we're running. One of the best things about getting older and becoming more senior is that I get to work with larger and larger teams, especially students. So everything I talked about today, all the good things and bad things, and is sort of a mixture of me and my students. So I'll take the credit for all the bad things, and the students get all the good credit. So from left to right, we have all my students, both in biostatistics and statistics at Michigan, and a researcher from Georgia Tech who I work with as well. And then I get to work with an amazing team of researchers. One of the best parts of mHealth is spanning the spectrum of statistics, computer science, behavioral science, and sort of medical science. So I work with a team including Susan Murphy, Billy, who are mDOT members. And then I work with statisticians like Snigdha and behavioral scientists and clinicians like Srijan Brahmaji, Mike Dorsch, and Jesse Golbus. And so this is just why I love mHealth in the area. So I'd like to talk to you today about the design of these treatment selection algorithms in mHealth. I'm going to give you some examples of the challenges that we have in designing these studies and designing these sort of algorithms. I'll talk a little bit about monitoring and deploying the algorithm. So I'll talk a little bit about, once we've designed it, what does it look like when you've deployed it? And specifically, how do we think about monitoring? And then I'll talk about post-study analysis. What can we learn from the data that we have? So in terms of the design, I'd like to start with a very simple example just to get everything motivated. So in the context of mHealth, we have many different types of mHealth studies. Here, I'm interested in mHealth studies where we're really interested in building just-in-time adaptive interventions. So here's an example called Heart Steps. It's a 6-week physical activity clinical trial. At this point, it's I think it was around 2018 when this was run. There's been multiple versions of Heart Steps since, but most of the versions of Heart Steps is focused on physical activity interventions to try and improve physical activity, where we have a wearable device, a Fitbit tracker in this example, and a mobile phone application designed to help improve their activity. And our question is, can we devise a just-in-time adaptive intervention? From now on, I'll call these JEDIs to help improve physical activity. So what is a JEDI? A JEDI is an adaptive intervention that adapts to your current context. In particular, we'll send interventions that try and tailor the content to your particular context. So in this example here, on the right-hand side, you might receive a message saying, asking you to do jumping jacks while you're cooking or something of that nature. Heart Steps under the hood is a sequence of observations, actions, and outcomes. So here is a diagram for Heart Steps. And what I want you to take away and what I'll focus on is this top row here. So in context of heart steps, we had 6 decision points per day where we had a potential to randomize an individual to receive an intervention. The observations including both the wearable information we're collecting on the individual as well as things through the mobile phone, specifically using GPS. We have things like your location and the weather at that location. We'll use that information in the course of 2 different components. So first, what we have is we have this R. So R here stands for randomize. In the context of heart steps, we randomized individuals on average to 3/5 probability receive an intervention. This 3/5 was chosen because it was thought that on average 3 out of 5 times a day, so on average 3 messages a day, would be seen as suitable or feasible, tolerable by the population that we were studying. Once we decide to randomize you to the intervention, we would then tailor that message to your particular weather, location, and time of day. So something that I want to disentangle to start is that even though the randomization in this simple example is not personalized, so it's always 3/5 probability, the message you receive is tailored. And so here, if it were raining outside, we wouldn't ask you to go for a walk outside. And so the content of the message will always be tailored to the individual's current context. What we're really interested in trying to achieve is a sort of an overall increase in physical activity. And the way that we want to achieve that is by improving proximal outcomes. So here, what we're interested in is improving physical activity in the next 30 minutes. And so our proximal outcome, or our sort of reward of interest, if we're talking in the RL context, is 30-minute physical activity. This diagram is sort of an under the hood look at what's going on in heart steps. And what I'll talk about now and the rest of today is really drilling down into this particular R component here and thinking a little bit about why we might move away from this simple coin flip in heart steps to more complicated decision rules. So specifically here, just to remind you, this randomization is very simple. It's just a 3/5 coin in which we have sort of a probabilistic dosage constraint on the system. But we might want to use an RL algorithm because we might want to build a more personalized just-in-time adaptive intervention. So here, we're randomizing, and the randomization does not depend on your current context, but we might learn from the data that we might want to increase the probability of sending a message in contexts where we find that these messages are beneficial. And we might want to decrease the probability of sending a message in settings where the message is not beneficial. Here, I put beneficial and not beneficial in quotes because we have to actually operationalize what we mean by beneficial. But just abstractly, if we see data on an individual and we see that, for example, on weekends, our messages are actually improving your step count significantly, then we might want to increase the probability of sending you a message over the weekend. But if we see that during the weekdays, maybe midday, you're just busy at work and so the messages are not effective, then we would want to decrease that probability. And so the RL algorithm is trying to use this ongoing information to actually improve the decision-making going on in this randomization scheme. However, there are trade-offs, and I think this is the key point that I want you to take away from my talk today, is that in the context of designing personalized just-in-time adaptive interventions, or as Susan has coined the term PJEDIs, there's a lot of trade-offs in building these. So the first trade-off is just a very simple one that all kind of RL algorithms have, which is a priori, we don't know the best action to take in each individual context. So this requires us thinking about the exploration-exploitation trade-off. In every given context, we have some information about whether or not it's a good idea to send you the message. And so in that way, we want to exploit that information. But we also have some uncertainty in that information and uncertainty about the best action. And so we want to have some ability to explore the space of possible interventions that we could provide in that context. And thus, there's a trade-off between exploiting the current knowledge and exploring alternatives. The tension here is that there are many different ways to operationalize the exploration-exploitation trade-off. There's a lot of work in reinforcement learning on different very advanced algorithms. One of the key design constraints in mHealth is the goal, it's sort of the difference from here than, say, in gaming or in robotics, is we don't have unlimited data. We have a clinical trial that we're going to run in which we have a finite set of individuals. And in particular, we don't want anything to be unstable in our deployment of these systems. And so one of the things that we value above all else is sort of algorithmic stability as a key engineering concern in the design of these PJEDIs. The other concern is a more statistical one, which is that many of these algorithms weren't designed for post-study inference. And when we're running clinical trials and we're thinking about collecting data in the context of mHealth, we're typically interested in answering scientific questions and performing post-study inference. And so we also want to make sure our algorithms are designed with the ultimate goal of being able to do science. So the first project I'd like to talk to you about, I have a few of these, is one in which here's just the standard RL setup. Here, what we have is an acknowledgement that in an mHealth context, individuals don't arrive in our studies one at a sort of all at the same time typically. Typically, what ends up happening is we recruit individuals over time, and they start at different moments in time. And so this picture here is to emphasize two things. One, when you're designing an RL algorithm, there are three main components: the current state, the state variables that we're deciding on, the actions and how we're going to select those actions, and the reward, the thing that we're trying to optimize over. The other thing I like this figure to highlight is just that the individuals are not being recruited simultaneously, but we'll observe a first individual maybe early on because they were recruited early on, and another individual will be recruited later down the line. And so one of the things we want to take advantage of is that there's information accruing before the second person arrives. And by the time we hit the 50th person in the study, we'll have 49 other individuals in the study already. So there are multiple challenges methodologically in the context of mHealth. And in particular, the four I like to highlight when you're thinking about RL agents. So here I have a state. I want to figure out what actions to take, and I have a reward. Well, there's four key issues. Number one, there's going to be heterogeneity in the treatment effects. So specifically, we expect that the effect of these actions to be different for different individuals. Not only that, but we expect these effects to be different across time. So we don't expect that the treatment effect to be not to be constant either across time or across participants. Second, even if we don't have treatment in the background, and we just look at the reward, this reward might be non-stationary, meaning it might just be changing drastically over time, no matter what treatments we provide. And so we have a lot of non-stationarity is sort of the statistical way of saying that. Not only that, we might have nonlinear relationships between the context we're observing and the reward. Lastly, we might have multiple individuals, and we might have to think a little bit about how we're going to pool information across them. So in our context, we're going to think about the similarity of individuals. Now, there's sort of two extremes of this. One is every individual is very, very different from one another, in which case you would want to treat each individual and learn only on that individual. In the other extreme, you have what we call homogeneous, or basically very, very similar individuals. In that case, you would want to pool all the data you've collected so far on all individuals and use all of that information to learn as quickly as possible. When you don't have those two extremes, you sort of have a trade-off. You want to pool some information across individuals to learn faster and reduce variance in your estimates, but you're going to incur some bias. And so what we came up with in this project was we used sort of a network structure to talk about who is similar to whom. And so we have a network that maps similarity across individuals. So we use this information to perform what we called ROME, or robust mixed effects. Here we modeled the treatment effect as a linear model in the state variables. But we allowed for the individuals, the users, as well as time to have specific effects. So here we have an additive model where we have a global fixed effect, we have sort of a random effect per person, and a random time effect. This model, this ROME model under the hood, has a couple other moving parts that I'll just briefly mention. Specifically, we use ideas from debiased machine learning, which allow us to capture the non-stationarity and non-linearity of the baseline reward. And we use what's called nearest neighbor regularization to allow us to smooth these parameters and smooth information across close individuals. So here, when I say nearest neighbor, I have individuals in my study. I have people who we think are more similar, and so they'll be close to one another, and therefore we'll pool information more. And we have people who are far apart, and they'll pool information less. And so this sort of nearest neighbor or network-based regularization allows us to get away from, say, standard random effects, where you assume that everyone is sort of similar to everybody else. The last part here is what we call Thompson sampling. So the way that the algorithm works under the hood is we actually use a randomization-based method based on Bayesian posteriors. And so this allows us to use the posterior distributions to allow us to gain information about these parameters and use that uncertainty in the estimates to do this exploration-exploitation trade-off. What I'd like to focus on here is just why we think this algorithm makes sense. So here on the left-hand side is a synthetic study of this algorithm against competitors. So here we're comparing it to a few other alternative bandit algorithms and showing it performs well. This is in the context in which you have heterogeneous data and you have a nonlinear reward. But we also wanted to see how well it did in terms of performing relative to other algorithms in the context of real data. And so we used a recent study called Valentine that Jesse Golbis and Brahmaji Nalamothu ran to understand the sort of relative expected rewards across these different algorithms. So the right-hand side is showing that Rome, when we use this algorithm, can often do better. Specifically, we really wanted to understand how well can Rome do when you compare it to, say, pooling-based algorithms that assume sort of a exchangeable structure across individuals and assume no temporal differences. So Intel pooling is that algorithm. And then standard is just assuming no pooling across anybody. And here you can see that there's enough heterogeneity that if you don't pool smartly, that you don't have much benefit of pooling in this example. Now, this gives us a sort of a hope that Rome is a good algorithm to use. The other thing I just wanted to mention in this time is that this isn't the only way to evaluate the algorithms. And specifically, if you go back to Anna Trello's good talk at mDOT, I think at this point a year ago or so, there are many ways to evaluate an algorithm in terms of its performance to think about whether or not it's a good algorithm to use in a future study. And here what we did is we actually didn't just want to understand the expected reward, which is sort of average-based performance, but we wanted to know if we bootstrap our data and think about multiple different pulls from that data set, for any particular data set, Rome might be almost as equal as any of these other algorithms, but on average just perform better. And so we wanted to understand if we compared in every bootstrap sample, how well could we do? We would want to see that Rome is outperforming almost all the time. And so the right-hand side, I have to credit Easton Hutch with this idea of building sort of a p-value or sort of performing a test statistic to say how often are we actually seeing Rome outperform these competitive methods, and the right-hand side is showing that it almost always was in this context. So there's a bunch of other challenges that I'm just going to highlight. Again, I think Anna's talk was great because I think it gave a framework for thinking about these things. I'm trying to give you a sense of all the different issues that we've come across and how we've handled them in specific contexts. So here are 4 other challenges that I want to mention that we didn't talk about in Rome. So specifically, we might have missing rewards. So the outcome, the reward that we wish we saw, in Rome, we assume it's always observed. However, it may be missing. And so I'll talk a little bit about that. Measurement error in the context variables can often occur. And I'm not going to talk about this, but I wanted you to be aware of it simply because there's recent work by Ziping Zhu and Yongyi Guo on the context of measurement error in context variables. There's also delayed effects that Thompson sampling ignores, and there's interesting work on using cost functions to capture delayed effects. And lastly, there's an issue of pooling with reproducibility. So specifically, if you're not careful in Thompson sampling, you can have issues about reproducibility. The one I'd like to focus on for the next 5 minutes is just this missing reward issue. So specifically, in a recent study, the intern health study that I've been working on, we were trying to design an RL agent. And in this context, there's a lot of missing data. So here, what we're interested in is understanding for intern health, we have 3 different agents we're going to build. We're going to build an agent around mood, step count, and sleep. Each of these agents is going to operate under the case of having a specific reward. And this plot is simply to highlight the fact that if you look at the if you look at the y-axis, this is the percentage of users with at least one non-missing observation over the course of weeks. And so if we look at the first 20 weeks, we can see that both sleep and mood, or sorry, sleep and step count have a drastic reduction or drastic increase in the amount of missing data over the course of the first few weeks. Now, with missing data, this means we might not be able to learn very quickly on individuals. And so we had to think a little bit about how we're going to handle missing data. And I'd like to give you just a brief idea of how we're going to do this. So the way we're going to do this is we're going to use historical data to build what we call synthetic surrogates. So the idea here is that we have, if our true reward is, say, 6-hour step count, we might want to use the Fitbit to measure it. However, we have surrogates for steps through the phone and other devices. So for example, if I have my phone in my pocket, my phone has some other measures of step count as well. And I know that those aren't the true reward, but I know that they might be good surrogates. And so what we'll have here using historical data is we'll build a predictive model that takes the surrogate information and predicts the true reward. Now, if this model that we're using for prediction is good, then it would be a good idea to use this prediction model as a way to impute missing rewards. However, we don't want to trust it fully. And so the idea here is in our new study, we'll always, if we observe the true reward, we'll use it, but we'll use the surrogates to build what we call a synthetic surrogate using the predictive model from the historical data. And then we'll use this prediction model and the synthetic surrogate and jointly model the true reward in synthetic surrogate to improve efficiency. So here the idea is that we can use synthetic surrogates, and the idea here is to use machine learning-based algorithms to build these predictive tools and use these predictions as alternatives to a true imputation model. In particular, when you do joint regression in this way, you don't have to fully trust the synthetic surrogate. But if the synthetic surrogate is good, you get a much more efficient estimation procedure, and this allows us to learn quite quickly. All right. I'd like to switch gears here. So those are the sort of methodological challenges we've come across in a recent few studies. I'd like to change gears and focus on sort of more the stability side of the equation, and then talk a little bit about data monitoring. And to do that, I'd like to switch gears and talk about a different study called Low Salt for Life. So Low Salt for Life is a recent study in which we're deploying an RL algorithm in individuals who are adults being treated for hypertension. So these adults were randomized to either app or no app, and they were given the app for 6 months. And within the app, we had individuals who, if they go to a grocery store or restaurant, so we would have to use GPS to actually do this, we use GPS to know if they're going to a grocery store or restaurant, and then we randomize individuals given their current context to either receive an intervention, a notification, or not. And the outcome or reward is, did the participant open the app within the 30 minutes of the randomization time? Here, and I know binary outcomes are often quite difficult to deal with because they have low information. However, we didn't have much to go on, and every type of more continuous outcome we tried to devise, it seemed basically would just boil down to a binary outcome. So we decided to just focus on a binary outcome. Now, for those of you who have not thought about how to build a Thompson sampler for a binary outcome, the key idea here is that you'd still think about your standard logistic regression. So you have a binary outcome, you have a context and an action. You're going to think about building a logistic regression and a Bayesian logistic regression. The key issue with Bayesian logistic regression is if you have a very, very rich context vector and you have very little data, you might end up having a very unstable fit if you just fit a logistic regression. This is called separation for those statisticians in the audience. And so what we ended up doing is we thought about how do we build a stable algorithm when we want to incorporate these ideas of pooling and shrinkage, or pooling information across individuals and fitting a logistic regression. And what we came to was work by Andrew Gelman in 2008, which introduced this idea of shrinkage priors. And so here is sort of a statistical tool to achieve algorithmic stability. The idea behind this tool is that instead of building priors which sort of are very, very weak, we build priors that, for higher order interaction terms, shrink the effects even more. And this allows us to have a very stable algorithm that no matter when we do the update will always give an output that makes sense and will not lead to sort of statistical issues when fitting these models. Not only that, we also came up with a procedure for coming out with the actual model we fit. So if there wasn't enough information about a particular variable, we decided to not include it. And this work was by Madeline Abbott. Madeline came up with a very nice sort of flow diagram, and we had to document all of this because it was a clinical trial. We have a nice protocol for how we thought about building this algorithm and building it to achieve model flexibility while also achieving algorithmic stability. The last thing I wanted to mention on this example is we had to think a little bit more about how to communicate with our software engineering team. So one of the things that I think when you're deploying or building a RL system On the statistical side, you might decide, oh, I have this very complicated, very nice algorithm that if I had a team that could implement it, we should be good to go. However, there's a lot of software constraints when you're designing an RL agent. And in particular here, we didn't have the ability to, in real time, rerun our software, rerun our Thompson sampler every single time for every context. So what we decided to do is we decided to build what we call the mega table, which is for every individual, we built a lookup table given the current context and reported the randomization probability in this lookup table. Now, is this the most efficient thing to do statistically? No, because the context could be varying, but this allows the software engineering team to write simple software which would just, for each individual, pull up that lookup table, look up the correct corresponding row in this table to get the randomization probability to use in the RL agent. And we found this to be a good way to have robust communication with the software engineering team. Inside of Low Salt for Life, this is actually the study that's currently being monitored, and we're currently running the study. So I wanted to talk a little bit about study monitoring in this phase. So I wanted to build upon Anna's very, very nice talk where she talked about when you're building an online algorithm, you need to think about different types of flags for the severity of those flags. So Anna's talk focused on red, yellow, and green flags, in which you have red flags where you want to safeguard individuals' data or the utility of the data, so some critical issue that you need to flag. Yellow flags are where the RL agent has an issue, or green flags are things that might affect post-study analysis. What I'd like to be is a little bit more concrete today, and specifically I'd like to talk about, while it's good to have flags that you've written out ahead of time in protocols, during the course of the study, we'd also need to look at the data every single week. And what we ended up doing is we built this really, really nice automatic report generation method. So Madeline, again, was the one who came out with a monitoring system where every single week she came out with a automatically generated report, which allowed us to evaluate whether or not there's different types of issues arising. So specifically, we used this report, and I will credit Rachel Tucker Gonzalez with this, of identifying critical, what we call red flag issues by using this report. In this example here, what we noticed is there was an individual for which we never sent the intervention. So if you see here cent equals 0 and cent equals 1 in the top table, you don't see any cent equals 1 in the bottom table. And this was a red flag that we had identified. And so we had a critical sort of team meeting the next day in which we realized that Apple had done an entire update to their system. The software engineering team had fixed some issues on their end that were a consequence of that Apple update, but in the process had broken the pipeline for sending messages. And so we had sort of a very, very rapid development on fixes to that issue. And so what I wanted to mention is, while the red, yellow, green flags are quite useful, what's been really, really useful for communicating with the clinicians, the software engineering team, and the statistical team are these reports which say out in words, and you can talk through things in words rather than just have them in the software itself. The second thing I'll mention is that there are cloud versions and local versions of the code, and what we monitored is differences between cloud fits and local fits to make sure there weren't any issues with the cloud implementation. One of the things we ran into is that a lot of these softwares rely on Python packages or different types of packages which might cause issues, and in particular what you can notice is that the cloud version will lead to slightly different answers, and so we ended up monitoring the different fits on cloud and local to make sure that there was no gross issues with those fits. The last thing that I'd like to mention that I think is underutilized in both RL-based mHealth studies as well as just standard MRTs is the use of calibration plots. So specifically, in all of these RL studies, we have individuals who are being randomized over time, and that randomization probability is also changing over time. However, we also need to think a little bit about whether or not the randomization probability that we are saying should be used is actually being used in the study. So in a simple example, if I had an MRT in which the probability of treatment was 0.5, it should be the case that if I looked at my data, 50% of the time I was sending messages and 50% of the time I was not receiving messages. Now, when you have a small data set, it won't be exactly 50-50. And so in those cases, you might have some variation around 50-50, and you want to understand that. Calibration plots allow us to do that for an RL agent. So specifically in RL, the randomization probabilities will vary across the range. So here we did some clipping at 0.1 and 0.95 or 0.975, I believe. And so here we had a range of probabilities that we could achieve. And within each of those ranges, we had different amounts of data being accruing. And so here what we plotted is we plotted in each of these ranges, we looked at the average number of times it was sent, and we built a confidence interval based on sort of a 95% confidence interval in the range. And we wanted to know how often is it in here. So if you look at the 0.50 to 0.55 range, we can see that, okay, on average, it was sent 0.50% of the time. However, if we go down one, we sort of see a disagreement. And so this allows us to think about whether or not the actual implementation of the randomizations was matching what we intended it to do. And this is a more statistical way to build sort of yellow flags. One thing you'll note also is that the amount of data in each of these buckets is very different. And so in particular, we have a flag that was raised in this bucket, but as Rachel pointed out, we averaged it to be exactly 0.825, but it would actually, this bucket was actually skewed towards 0.80. So if you actually do the correct test, this red curve, this red bar would actually not be a problem. And so this allows us to talk about whether our algorithms that we're designing are actually being implemented correctly. And I think this issue, which I call misdesigned probabilities, is actually a big issue in mHealth, in which there's a lot of front-end discussion around what the probability should be or what the RL algorithm should be, but there's less checking on whether or not the actual randomizations that are happening are well calibrated and are achieving those randomizations that you set out to achieve. So by that I mean in certain studies, and I will say in certain studies, I have seen a design in which they said, I think that the probability should be 0.75 or 0.6. But when you look at the data after the study clearly was not randomizing at that exact number. And calibration plots allow us to ask these questions while monitoring the study rather than asking these questions after the study was run, and identifying any serious red flags where we're going to have to think about whether or not we actually deployed the RL agent we thought we deployed. The other aspect of monitoring that I just wanted to mention briefly, because this is something that's come up more recently for me, is data safety monitoring boards and reporting RL agents to data safety monitoring boards. So specifically, this is less about monitoring for red, green, yellow flags for the purposes of the study, but more about how do I report these types of algorithms to data safety monitoring boards. And what we've worked on is we've thought a little bit about understanding how much variation these algorithms have across individuals and across contexts. And so what we built is sort of a report for the DSMB that allowed us to sort of understand and report out changes to these probabilities over time, to talk about how extreme or whether or not they are extreme, as well as using those calibration plots. This allows us to have more visual ways of communicating with DSMBs and allowing them to feel comfortable with these RL agents while deploying them in settings and understanding the safety implications of these RL agents. I won't talk more about these here, but I think this is sort of a crucial issue as MRTs and RL agents are deployed more and more in certain areas, specifically in areas like suicide research, where data safety monitoring boards are very, very aware and very, very keen to be aware of any potential severe adverse events and their relation to the RL agent. Okay, with the last about 10 minutes or so, I think I just wanted to mention a few issues around post-study inference. So the first 25, 30 minutes of my talk has been focused on how to think about the different issues involved in deploying and monitoring an RL agent. Now that you've run one of these studies, how do we actually analyze data coming from a RL agent-based mHealth study or an MRT? To do this, I wanted to introduce a causal effect that Susan Murphy introduced in 2018 with Audrey Berufka, namely the causal excursion effect. This is a moderation analysis that's been introduced for the understanding of causal effects in the context of mobile health studies. This effect, in statistical terms, we call it a causal excursion effect because it is an effect which is causal. So if we look at this equation here, I'll say out loud what it's looking at. The interior is looking at the difference between treatment and control, or message and no message, conditional on the observed history. So When we look at this contrast, it's what is the amount of steps you take in the next 30 minutes, given I treated the individual and their observed history, subtracted off from the expected number of steps in the next 30 minutes, given we said no message and the exact same observed history. The effect then marginalizes over HT, so meaning we're looking at something like an average treatment effect in the sense that we're averaging over the observation history, on a few potential moderators of interest. So here, ST is just denoting that set of potential moderators. And so we talk about this effect as a causal excursion effect because it's causal in the sense that it's a contrast between two different effects on the proximal response following a decision point T. It's conditional because you're conditioning on potential moderators. So a simple example would be conditioning on a thing like weekday versus weekend, positive, the value of the positive affect, how many steps were in the past day. These are different potential moderators you might condition on. It's marginal because you're marginalizing over HT, and we call it an excursion effect simply because you're averaging over HT, and HT includes prior treatments. So these effects often will be dependent on the randomization scheme you use, and therefore is sort of thought of as an excursion from that effect, or sorry, an excursion from the policy you implemented. So here, what's been done historically is we've used regression-based methods. So I'm showing this again. I said to Vivek at the beginning of the talk, I'm a statistician. I reserve the right to show a few equations. For those interested, this is called a weighted center least squares. I would like to just explain it in very broad terms as a sort of regression where you're regressing y against a potential model for y given the history and the action, and you're interested in estimating these causal excursion effects. What we notice is a few things, and I just want to mention them out loud. First, the original WCLS, we had an issue where with missing data specifically, we had to think a little bit about, well, this model is not robust to missing data. Namely, when we have missingness in our outcomes, we have to think a little bit more carefully about this modeling step. And so the first thing we've come out with is a robustness to this missing data. For those of you who are interested on the ML and statistical side, these ideas come from the sample splitting, debiased machine learning ideas, in which we actually will build models using machine learning to build out these nuisance functions. For those of you on the behavioral side, the idea here, you can just think about it as when you have missing data, you have to think a lot more carefully about the modeling phase. When you have to think more carefully about the modeling phase, you might want to think, well, if I have to build good predictions, I might want to move away from linear models and use more machine learning models, which are designed to do good predictions. And this extension of the WCLS approach allows you to do that, which means you can bring in your machine learning collaborators and the prediction tools that they've built to do a better job in terms of estimating these causal excursion effects. Not only that, but we had to add robustness to these misdesigned probabilities. Namely, when you're running an RL agent, there is a concern that the way the randomization happened wasn't exactly how you saw it. And this has happened in the past where I've noticed that the randomization probably that was implemented, it can be slightly different than what you thought it was. And so we wanted to add robustness to this sort of probability not being exactly equal to what you thought. And so these approaches are also robust to those issues. The last issue I wanted to raise is one in which we have, I'm going to skip the slide, is one in which we had an individual who wanted to run exploratory data analysis. So when we're thinking about post-study analysis, we're often thinking not just about one particular primary analysis, but we're thinking about a sequence of analyses to inform a future study. So when I say that, what I mean is I have a primary analysis for an MRT in which I might assess a average time varying effect. Is there an average effect over time of the message versus no message? After that, I might want to ask, well, are there any potential moderators that I might want to think about? And if they do moderate the treatment effect, those are good candidate tailoring variables for a future RL agent. So what individuals have done in the past is they've started with a list of potential moderators, and they go one by one through that list, and they look at which ones are significant in single moderator analyses. So they run a sequence of exploratory analyses. The issue with that is it can lead to a lot of false positives. And so working with Snigdha Panagrahi in the stat department and her students, Shoham Bakshi and Yiling Huang, we sort of tried to think about how do we want to actually perform exploratory analysis to do moderation analysis where we're actually building those correct tailoring, finding out those correct tailoring variables without having a lot of false positives. What this led us to is to think a little bit about maybe our moderator list we want is quite large. So we have an exploratory analysis in which we have a lot of candidate moderators and a lot of candidate tailoring variables. And we want to perform a first stage selection. So here what I'm saying is I don't want to just fit this model, but I want to select a subset to focus on. When you do that, you actually have to then, if you wanted to do inference after selection, you have to account for that selection phase. And so Snigdha and I worked on what's called selective inference framework for exploratory data analysis. And we applied it to this Valentine study. So here's the Valentine study. If you remember the heart steps diagram, it's almost identical to the heart steps diagram. It's just in the context of cardiac rehab patients. So here you randomized 3/5 probability every single day, and the messages were not all, they were all anti-sedentary notifications. We ran the primary preliminary analysis for the causal excursion effect. So if you've seen these before, this is sort of a standard time-varying treatment effect that you would see in any MRT analysis. Here, we did it where we looked at different phases of the study. And what we saw was early on in the study, there was some significant effect, and that effect dissipated over time. And this is a very common thing to see in MRT analysis. However, what we wanted to do, and what Jesse and Brahmaji, who were the PIs of this grant, wanted to do, is look at a bunch of potential moderators. And when we made the list, what we realized is if we went by one, it'd be hard to then come up with a finalist for a future RL agent. And so what we instead did is we built a large list of about 25 variables. We performed moderator selection. And so for those of you familiar with the lasso and other methods like that, we ran a lasso algorithm to select potential moderators, and then we did inference that corrected for that selection step. And so what I'm showing you here is confidence intervals for the selected parameters. When we had 25 candidate moderators, we selected 5, and now we're looking at confidence intervals for each of them. And what I found interesting about this is that while when we were looking at time-varying effects, we thought that time mattered a lot. When you run these sort of non-individual, but you run these sort of joint analysis of all 25 variables, different variables pop out than you thought might. So here what we noticed is that baseline steps is very important, as well as the aggregated step counts taken during the prior week. Specifically, if you look at these two, you see baseline steps as a small positive effect, meaning if you walked a lot early on in the cardiac rehab program, this was sort of a good reason to send you messages. It was a positive effect. But if you've walked a lot recently, meaning the person's been currently very active in the prior week, then it actually has a negative effect, and that negative effect sort of offsets that baseline steps. And so really, it didn't really matter. And I should say one more thing, which is the aggregated walking distance was also the measure that was selected. So notice none of these variables are time and study variables, but instead are variables all around how much you walked at baseline, how much you walked in the prior week, and how much have you walked sort of so far during the study. This means that really time and study isn't a good candidate moderator, but instead these other variables might be good candidate tailoring variables for a future RL agent. These inferential guarantees allow us to pick out those that are actually significant as opposed to those that are not significant, like step counts recorded in the 30 minutes prior. So I'm going to end with one more statement, and then I'll save the last 10 minutes or so for questions and discussion. So specifically, I get this every time I give an mHealth talk, and I talk a lot about RL agents, and I talk a lot about the sort of complexities of building and deploying an RL agent. Specifically, people ask me, do I think that mobile interventions and just-in-time adaptive interventions through digital devices is sufficient, is enough? And my key point is no, I typically don't think that's true. In most settings in which you're deploying a digital intervention, it's in the context of a larger intervention package. In particular, there's usually static components of the intervention package as well as dynamic components of that intervention package. And we often have scientific questions about the integration of digital interventions with other kinds of human-delivered components. And to that end, Billy Nahumshani and myself have thought about hybrid experimental designs to answer questions about the integration of human-delivered and digital interventions. So I wanted to present you at least one example of that. So for those of you who are moving in these directions of digital interventions in the context of time varying, and other components. This is a hybrid smart MRT design in which we are looking at a weight loss study. And here we're randomizing at baseline to an app or app plus coaching, and we're randomizing again at 8 weeks, depending on response status. Within each day, we're also randomizing people to message, no message. And so in the future, we could see an RL agent being deployed in which this randomization at the level of the day level messages is actually using those techniques, those RL agent techniques, those bandit algorithms that I talked about before, but in the context of a smart study in which we're actually dynamically adapting interventions, both at baseline and depending on non-response at week 8. And so this example here, if you're a non-responder, we had different modest and vigorous step-up routines that we would randomize individuals to, and we were interested in not only the effects of the MRT and the SMART separately, but also their integrated effects. And so I think the future of digital interventions is not just deploying the RL agent and optimizing that agent by itself, but really thinking about optimizing that agent in the context of a larger intervention package and building decision rules at the level of the SMART, sort of the human-delivered intervention rules that interact with the RL agent more systematically. All right, so I'm going to end with a quick summary of my talk and then open up to questions. So my talk was focused on 3 different components of the sort of, we'll say, mHealth life cycle, specifically on the design of RL agents, the deployment of these agents, and post-study analysis. My goal when talking about design was to emphasize a few things, so specifically to emphasize the methodological challenges. So in the context of the Rome paper, those challenges were things like nonlinear baseline, heterogeneous users, time-varying effects. In the context of the intern health study, these were things like missing data, missing rewards, how to think about surrogates, and using predictive algorithms to build synthetic surrogates. And then also in the design phase, thinking about stability and robustness of these algorithms when you're deploying them in real-world settings. And specifically for stability, thinking about ideas of hierarchical priors in the context of our low salt for life study, and using shrinkage priors to build stability in complicated Bayesian algorithms. The second thing I talked about was deployment. And specifically, my goal here was to emphasize 2 different things. Number one, yes, we should have red, yellow, and green flags, but we shouldn't just rely on automated monitoring. We should rely on human-in-the-loop monitoring in which we have constant reports being read through by individuals to monitor what's going on in the RL agent. We've noticed many, many flags that have just been picked up through this automated monitoring and automated report generation process. Specifically, we've noticed that these reports help a lot with communicating across a very diverse team. We have software engineers, we have clinical domain scientists and statisticians, and the reports allow us a way to communicate not just in code, but also in the written word, which really helps us disentangle these issues. The other thing I wanted to communicate in sort of monitoring was the calibration plots and the use of calibration plots to monitor not just are there bugs in the code, but also using statistical tests to discover bugs in the code. Often it's not just the thing did not work, we got, that there is a bug, it's breaking, but also there's sort of hidden bugs that can happen on the statistical side that can only be picked up through statistical testing. And calibration plots are one way for us to really look at and understand, is this RL algorithm doing what we think it should be doing? The last part of my talk was on the post-study exploratory analysis, and my goal there was to emphasize 2 things. Specifically robustness to missing data and misdesign probabilities, as well as efficient inference for exploratory data analysis. Specifically, how to think about if moderator selection and accounting for complicated selection routines in the inference. So we have these selective inference techniques that we've developed. The last thing I will say is that I didn't get to talk about it today, but there's been a lot of recent work, again, by Easton Hutch, on data integration techniques to use multiple data sets to actually perform even more robust and efficient inference. The last thing I emphasized in my talk was that I do not think digital interventions are a panacea. I do not think that they're by themselves going to be effective unless they're built into an overall intervention package that incorporates human-delivered interventions. And I introduced the hybrid design, which Billy and I have worked on, that incorporates them through different techniques. Specifically, I gave an example of a smart MRT that incorporates human-delivered interventions that are adapted not only at baseline, but also based on non-response status. The thing that my talk focused on was sort of the technical details, and once you're in the world of these different algorithms, the kind of issues that could arise. But the thing that I want to emphasize is that the most important thing is the scientific question and picking out the right experimental design for that scientific question. I think there's many situations in which people say, I would like to deploy an RL algorithm, or I want to run an MRT, and they forget to start with, what is my scientific question? And I think the goal of today's talk was, once the scientific question leads you to the path of wanting to design an MRT in which an RL agent is being deployed, these are ideas that you should be using. But that does not stop you. That should not be the first point in your journey. You should be starting with, what kind of questions am I asking? And are these the appropriate tools that I need to answer this scientific question? And with that, I'll end. I think I have about 7 minutes or so, and thank everybody for listening, and thank Vivek again for the invitation.
Walter, terrific. Thank you very much. I'll open it up to the floor. Shaheen, could you unmute them so they can post their questions?
Participants may now use and unmute your microphones if you have a question.
Hey, what? It's Dominic. Sorry, maybe I should just show my picture. Yes, very, very nice talk. I love it. Just a couple of questions. So first question is for missing data. You talked about earlier. Can missing indicator be part of state variable when you build up this intervention? So.
Yeah, no, it's a great question. So I think, let me go back to the slide. So I think there's two different versions of missing data, right? So to your point, there's missing rewards and there's missing context variables, which measurement error is one example, right? And I know Ziping and Young Guo have a nice paper on measurement error. When you have missingness in the context variable, so for example, you wanted to measure prior step count in the 30 minutes prior, or maybe yesterday's step count, right? It was a measure, but they didn't wear the device yesterday. We do use an indicator of missingness as part of the context itself. Okay. And so we will build in those missing data indicators as part of the algorithm.
Right. So basically, like a missing data can be informative, right?
Exactly. Exactly.
That's great.
I think
yeah. Go ahead. Sorry.
The only thing I was going to say is on the missing rewards, the idea here had been, if we have missing rewards, it's a little bit trickier, right? Because it's a post-decision thing now. But there we were realizing we have other measures, specifically, for example, step count and sleep. We have measures coming from the phone, but we don't want to trust them as exact proxies, like exactly the same. And so we wanted to come out with a slight sort of synthetic surrogate way of mapping one to the other, but not exactly trusting it directly.
Yeah. Yeah, I'm sure like this is related to this double robust construction when you use auxiliary information, try to help impute the missing data. So
yeah, no, exactly.
Yeah, great. My second question, I think we talked about a little before. Do you have any idea, because you have been talking about this proximal outcome, but obviously people are interested in the distal outcome, right? So have you done anything related to this?
So I think right now most of the agents are really focused on the proximal. There has been some focus on distal. I know the issue is when you're designing these, those are like really delayed rewards. So the big issue is, how are you going to learn while waiting for these delayed rewards? So in the example of heart steps, right? Or I guess I'll give I guess we could use heart steps as an example. Most of these physical activity interventions, the delayed reward, right? You're often focused on something like a discounted version of the step count, and you might go for something more like a Q learning method, or something involving some Markov decision process kind of approach. The biggest issue there is often the delayed effects are really, really hard to learn given the data you have, and you have very limited amount of information. And so often what I think people do in practice, I think I have here, is they'll try and incorporate those delayed effects that you would capture in in one of those settings into the reward construction itself. So specifically, instead of looking at just the 30-minute step count, they would look at something like, is the treatment effect above and beyond what I think the delayed negative effects might be? And so they'll estimate those delayed effects either through data that they have historically, or they'll actually just use some type of clinician discussion to decide on what a treatment effect needs to be big enough to offset potential negative delayed effects.
Great.
Yeah, the only thing I'll say on that too is if the distal outcome is very distal and you don't have it as sort of an MDP setup, but you have it more like just a single value you won't see for a while, so like a weekly or a monthly measure that you don't have access to directly, there's some work, I know Kelly Zhu has some work on trying to actually predict it given sort of information you've collected so far and build some type of sort of local proxies, but really target that more monthly value.
Great. Thank you.
Yeah, of
Very
course.
nice
Thanks
talk.
for the question.
Wonderful. We have a few more minutes. Anybody else with questions? Looks like our statisticians tend to be on the quiet side. They speak with data.
Exactly. And they will send me emails asking me plenty of questions after, I assume. So there we are.